Have you ever thought about it when you step hard on the gas pedal at a traffic light? Listening to the captivating roar of the engine at that moment, your gas money is actually burning furiously. What's even more cruel is that the fuel you paid for, over 60% or even 70% of its energy, is not used to propel the car forward at all, but turns into useless waste heat dissipating into the air. We are always romanticized by the roar of large displacement combustion cars and the jerk of mechanical shifting. But if we strip away this emotional coat and look at it from a purely physical and mechanical engineering perspective, you will discover a cruel truth: the era of combustion engine cars should have ended long ago. This is not a forced push by governments for environmental regulations. It is simply an inevitability of mechanical engineering evolution. Electric vehicles replacing combustion cars is built upon ironclad scientific data and a physical dimensionality reduction attack. In today's video, we are not talking about carbon emissions, nor are we talking about intangible green ideals. We simply break it down from the most hardcore mechanical principles, thermodynamic properties, and the power output curve that drivers care about the most. To explain why electric vehicles are destined to dominate the future, I will divide the whole video into 5 sections to discuss in depth. Section 1, we ruthlessly uncover the thermodynamic truth of internal combustion engines. Section 2, a direct, head-to-head showdown between the torque curves of combustion engines and electric motors. Section 3, discussing why the deified gearbox is merely a life-prolonging elixir. Section 4, bringing out the actual maintenance ledgers of high-mileage boss-level cars on the internet. Section 5, a direct confrontation with the ultimate myth that replacing batteries costs hundreds of thousands. The content is very solid. Let's go straight into the first part. Let's talk about the thermodynamic tragedy of the combustion engine first. In the engineering world, the definition of efficiency is how much of the total input energy ultimately becomes mechanical energy to drive the wheels. The working principle of a combustion car, to put it bluntly, is installing a continuous explosion control room at the front of the car, injecting fuel, mixing it with high-pressure air, igniting it to explode and push the pistons. It sounds precise, but it hides a physical ceiling that human technology cannot break through, called the Carnot cycle limit. No matter how complex the variable valve timing car manufacturers use, or direct fuel injection, the thermal efficiency limit of internal combustion engines in mass-produced commercial cars is firmly stuck at around 40%, and that can only be achieved while cruising at a constant speed on the highway. If it's stop and go in the city, the efficiency will plummet to below 20%. So what about the remaining 60 to 80% of the energy? It all turns into waste heat and noise and is wasted. Part of it is expelled from the exhaust pipe, while the other part relies on the radiator fan for forced cooling. When you spend $1,000 to fill up the tank, more than $600 is used to contribute to global warming and prevent the engine from melting. In terms of engineering design, this is an extremely inefficient energy conversion process. In contrast, electric vehicles have a simple and crude energy conversion path. The high-voltage battery outputs direct current, which is converted into alternating current through an inverter, directly driving the motor rotor to spin. No violent explosions, no reciprocating piston friction. The energy conversion efficiency of an ordinary electric motor can easily reach 85% if an advanced silicon carbide inverter is used, coupled with a permanent magnet synchronous motor. The efficiency under daily driving conditions easily exceeds 90% for every kilowatt-hour of electricity you charge into the battery. The vast majority honestly turns into forward momentum. This huge gap in energy utilization rate is a physical barrier that combustion cars can never overcome. Next, we enter the second part, the huge difference in torque characteristics. Torque, also known as twisting force, determines how fast you are at the moment of starting and how strong the pushback feeling is when overtaking. Combustion cars have an ironclad rule: engine power is very weak at idle. If you want explosive power, you must step on the gas pedal and patiently wait for the RPM to rise to 3 or 4,000 to reach the point of maximum torque burst. The torque curve of a combustion engine is like a steep mountain peak. It requires a long climb to reach the top, and the time spent there is extremely short. This means the effective power range of a combustion car is very narrow. In city traffic jams, RPMs can't go up, so there's no torque. To overtake on the highway, you have to downshift first and wait for the RPMs to climb. This kind of power lag is an innate physical limitation, but the electric motor is a monster from a completely different world. The torque characteristics of an electric motor allow it to output 100% of its maximum torque directly from the moment the RPM is 0. When you step on the accelerator at a traffic light, high voltage current instantly passes through the stator coils to generate a strong magnetic field. The rotor is tightly gripped by a powerful electromagnetic force in milliseconds and spins wildly. No need to wait for fuel-air mixing, no need to wait for ignition. Its power response time is on an electronic level, creating an extremely broad torque plateau for electric vehicles. from the 0th second of starting, all the way to near top speed. The motor can maintain high power output. This characteristic of being strong across the entire range is the key to why electric vehicles completely crush combustion cars in driving dynamics. Having understood torque, we move into the third part: why combustion cars need gearboxes and electric vehicles do not. Many people think the gearbox is the pinnacle of automotive craftsmanship. Things like 10-speed dual-clutch PDX sound extremely high-tech, but to be honest, the gearbox is just a crutch to cover up the innate defects of the internal combustion engine, because the effective torque range of the engine is too narrow. If there were only one gear ratio, the car would either have a top speed of only 50, or not even be able to climb a slope from a standstill. Engineers had no choice but to stuff in a whole gearbox full of complex gears. Through frequent gear shifting, they keep the engine as much as possible on that small torque peak. This significantly increases the weight of the car and drives up costs, while also bringing shift shock and high maintenance FEs, because electric vehicles have maximum torque at 0 RPM, and their maximum RPM easily reaches 15,000 or even over 20,000 revolutions per minute. They possess a bottomless power bandwidth. They only need to be paired with a fixed gear ratio reduction mechanism to perfectly cover the requirement from 0 to 200 kilometers per hour. No complex clutch plates, no planetary gear sets. As fast as the motor turns, the wheels turn. Power transmission is direct and smooth. Removing the gearbox reduces weight and completely eliminates the component in traditional cars most prone to expensive breakdowns. In engineering terms, this is an absolute evolution. Part 4, let's put theory aside and look at real high-mileage boss-level cases on the internet. For traditional combustion cars, noticeable power degradation at high mileage is destiny. Piston ring wear, valve carbon buildup, oil pressure decline. The accumulation of micro wear makes the torque plateau even more fragmented. But what about electric vehicles? German owner Hans Jürgs, Tesla has surpassed 2 million kilometers in mileage, according to the dismantling of retired high-mileage motors by European engineering institutions. Aside from normal physical wear on the bearings, the electromagnetic conversion efficiency of the stator coils and rotor has virtually zero degradation, because there is no high-temperature piston explosion and friction. The magnetic field strength won't significantly weaken over time, whether it's 50,000 or 500,000 kilometers. Stepping on the accelerator still yields maximum torque at 0 RPM. Next, let's look at the most cost-sensitive commercial fleets. The US Tesla fleet has multiple cars with mileage over 600,000 kilometers. Operational ledgers show that combustion cars require frequent oil changes, spark plugs, and transmission fluid. After 100,000 kilometers, you also have to worry about turbocharger oil leaks. Electric vehicles only check coolant and replace cabin air filters every 20,000 kilometers. Thanks to the kinetic energy recovery system, releasing the accelerator turns the motor into a generator to decelerate and charge. The original brake pads still have half their thickness left after driving 300,000 kilometers. Calculating it out, the operation and maintenance cost per kilometer for an electric vehicle is only 1/3 of that of a combustion car in the same class. Finally, we come to the fifth part, the ultimate big question. If you drive an electric car for a long time, the battery will inevitably break. And won't replacing the whole thing for hundreds of thousands ruin you financially? This fear is built on a misunderstanding of mobile phone batteries. Mobile phones don't have active cooling and are often fully charged and completely drained. But an electric vehicle chassis has an extremely precise battery management system and a liquid cooling thermal cycle. Like a nanny, it controls the battery temperature at the most comfortable Celsius, 25 to 35 degrees, and reserves hidden capacity to prevent overcharging and over-discharging. Big data from hundreds of thousands of owners globally shows that after mainstream lithium battery electric vehicles travel to 100,000 kilometers, their average health status remains between 88 and 92%. When a combustion car's engine leaks oil and needs major repairs, an electric car merely has a slight reduction in full charge range, which does not affect daily commuting at all. What if it is indeed partially damaged? Through dismantling videos on foreign real repair channels, we can see that modern batteries have a modular architecture, connected in series by dozens of independent modules. When computer diagnostics show an issue, it's often just one module malfunctioning. You don't need to spend hundreds of thousands to replace the whole pack. Third-party engineers just need to accurately extract the damaged module, replace it with a healthy, good one, and perform voltage balancing. The entire big battery is then restored to full health, and the cost drops directly to tens of thousands. Even if the large battery ages to 70% and is unsuitable for car use, it remains a highly sought-after commodity in the second-hand energy storage market. It has an extremely high recycling residual value, which can directly offset the cost of replacement. In conclusion, when we use thermodynamics to see through the waste of internal combustion engines and use the God's eye view of an electric motor's maximum torque at 0 RPM, to examine the narrow power band of combustion cars, then see the minimalist reliability of removing the gearbox, as well as the high mileage, incredibly economical maintenance ledgers, and modular repairs. Electric vehicles replacing combustion cars, just like digital cameras eliminating film cameras, is the purest physical dimensionality reduction attack at the foundational technology architecture level. The roaring sound of a combustion car will become a classic work of art in a museum, but as the ultimate tool for daily commuting and transportation, electric vehicles have already secured all tickets to the future. This is the final answer given by physics and engineering.